Kind of would
Okay, everybody. When we discuss kinematics and the motion of something, or forces, or drew free body diagrams, and all that stuff, remember that when we're talking about translational motion, we're interested in really only one point on the object. Okay? We're talking about the translational kinematics, translational dynamics, F equals ma, and the translational part of energy. We are interested only in one point, and that's this point right here. Okay? Just the center of mass, and that's it. Okay? Only that one point is what we're describing. Okay? If you want to know about the individual points on the object, then what you need to do for translational motion is you literally have to break the object up into little parts and analyze each little part and all the interactions between each of the little parts. Okay? So like if, like we did in aerospace engineering, if we had a plane, we would take the plane and we would chop the thing up into a big grid. Okay? Each one would have its own center of mass. And each one would interact with all the other parts around it through the internal forces, the stresses and strains, or the tensions and compressions and all that sort of thing. Okay? So we can analyze each little part. If you look at the object as a whole, all you're gonna look at is just that, just the center of mass, the entire thing, right? It wasn't until we got to rotational motion that the extended part of the object made any difference, really. Okay. All right. So all the trajectory motion we talked about when things are flying through the air, it's just the center of mass that we're describing, not the extended part of the thing flopping around. So like you take a gymnast and the gymnast tumbles through the air, only their center of mass is following that parabola. Okay? All right. So once again, we've already talked about this, but center of mass. Center of mass. Okay? How do we calculate center of mass? Do you remember?
Sum of mr squared.
Sum. Oh, okay. Do it that way first. The sum of the mr squareds
over
how much mass, total mass there is, right? Over the total mass of the sum of all the masses, okay? Now that's if it's a discontinuous object, like you have a little piece of mass out here, a little piece of mass out here, and a little piece of mass out here, and they're connected by something that has no mass, right? Or very little mass, okay? All right, but if it's a continuous object, if it's some continuous blob, okay? Then we have to integrate the thing. Yeah.
Is it not just MR? Or is it squared?
It's just
Oh, you're right. It's MR. Thank you. What is MR squared? That's moment of inertia. We're not moment of inertia. We're just center of mass. That's right. Because this is going to give you a location. Because mass over mass, kilograms over kilograms, is going to cancel, leaving us only with a location, right? So my mistake. That's MR. It's right here in my notes, and I didn't even look at it. Okay. So if we have a discontinuous object, a lumpy mass object like this, if we have a continuous object, it's the integral of r dm, or the integral dm. Okay? And there you go. Now we will do a couple of those each. All right, we talked about that. F equals ma. Remember in F equals ma, remember we're only talking about the center of mass. You might want to mark that down. Okay? And when we're talking about kinetic energy, If we're talking about kinetic, I'm talking about 1/2 mv squared. We're only talking about the motion of the center of mass. If we're talking about potential energy, spring potential energy, we're talking only about 1/2 kx squared, and we're talking about the location of the center of mass. Okay? We're talking about gravitational potential energy, mgh. Once again, we're only talking about the location of the center of mass. Okay? It wasn't until we got to rotational kinetic energy that we had anything to do with the object's shape that made a difference. Okay? One quick thing about potential to be aware of, and we had this problem in our last test, is if we have an object that's like this and it's going to rotate like this, please be aware that this object has a center of mass. Okay? Its center of mass is somewhere over here. So when this object rotates to its new location like this, the center of mass moves to here. So we're only talking about the height change of the center of mass. Okay? All right. In the problem we had a massless bar and a mass m over here, and a mass essentially of 4m over here with the bug on here, right? Yeah. When it rotated, everybody was looking at just this 4m and neglected this little m up here, right? Okay. Now you can get by without figuring out the center of mass location if you just figure out the potential energy change of each individual piece of mass. So like this one has a change of mass of, I think it was L, right? And this has a change of height, this has a change of height of L. It decreases L, right? That's its change in height. And this one over here had an increase in L, right? Because it moved upward. All right. Or you could just figure out the center of mass of the object to see where the center of mass goes. Okay? Either way. So, like when we have this object, and this object is pinned here, and it spins and moves downward. If you're going to use conservation of energy, it has potential that turns into kinetic, okay? Gravitational potential that turns into some sort of kinetic down here, right? No matter what kind of kinetic it turns into, you need to know this is the center of mass location, okay? So it goes from here to here. Not this entire length, okay? Just the center of mass. All right, a couple other things pertaining to center of mass. We've already talked about some of these things, but here's another couple examples. Okay, so say you're lobbing bombs at your enemy over here. Okay? They're your enemy, you can tell because they're evil. Alright? And you're shooting this bomb over at this person right there. That's right. It'll smash them even if it doesn't go off. Alright, so here's the center of mass of the object. But unfortunately, you throw it slightly too soon, and so it explodes right here. It explodes into pieces. Okay? Alright, even though the object explodes into pieces,
it still has the same center of mass, wouldn't it? Yeah.
Right. It still has the exact same center of mass. And so, if you aimed it to land on this person, the center of mass of the object will still land on the person. Yes.
What if,
But there might not be anything there. That's correct.
Yeah, what if something impeded some of the shrapnel? Like if it went through like a really dense cloud, or.
All right. Well, if there's an outside force on the object, like drag, if there's an outside force on the object, like drag, then this wouldn't follow a direct parabola, right? Okay. And so that could happen also on some of these pieces as well. That's exactly right.
But we're not going to deal with that?
What's that?
We're not going to deal with that?
No, because that actually gets exceedingly complicated. Very, very quickly. In fact, you notice that we didn't do any drag problems that, unless they were one-dimensional, right? Either moving this way or this way only. Drag problem in 2 dimensions is actually quite complicated. It can be done. It's not that bad. It just takes a lot of math. And so we've got the basics of it. That's as far as we want to go. Essentially, it would be taking this drag problem and this drag problem, or this drag problem actually for trajectory motion, and adding them together. And you could do that with x motion and y motion at the same time. So it could be done. You'd have 2 time-dependent integrals at the same time. Connected. Yeah. So, yeah. So let's say this thing breaks into 2 pieces. Okay? We'll do that. We'll jump over here and we'll do this problem. So here's our problem. Here's the bad enemy who we don't like. And we're going to launch this thing at 50 meters per second. And this angle right here is 30 degrees. Okay? First off, I want you to tell me, where is this person? If we've launched it to land right on that person, where is that person?
V squared sine 2 theta, right? Over G.
I don't know.
2 theta over G.
Yeah.
What is it?
V squared sine 2 theta.
Range equals v squared sine 2 theta over g. Now, if you don't remember the range equation, because that is not on your equation sheet, and quite frankly, I don't remember it until students tell me it again, then just remember this, that in the y direction, by the way, if you have a problem like this, what's almost always, unless you know the range equation, what's the very first thing you do? Now you split this into components, right? And so the initial x velocity is going to be, what, 25 times the square root of 3? And the initial y velocity is going to be 25, right? Meters per second. Okay, now the key thing is, that's a special triangle, 30, 60, 90. The key thing here in the y direction is you know a lot of things, right? In the y direction, you know the initial y velocity is 25 meters per second. And you know the landing velocity. What's the landing velocity? Negative 25 meters per second. Okay? You know its starting location. Where's it beginning? 0. And you know where it lands. What landing height is it? 0. Okay, with that information, now you know one other thing. What's the acceleration? Okay, that's not good enough. I need a number.
Negative 9.8.
That's not good enough. Thank you. Negative. I think some of you were saying it already. I might have missed it, but negative 9.8 meters per second squared. Why negative?
Because it has to be opposite to the starting velocity.
I've already defined up as positive when I put this number down, right? I defined that as positive and down as negative. And so with this, which equation would I use to find the time?
V squared equals V squared plus 280. That doesn't even have t in it.
Yeah. V squared equals V naught squared plus 2ax minus x naught, or the y equivalent of that, right? Now that one won't work because we don't have time. We're looking for time that doesn't have time in it.
X. That's the one I meant. I just didn't say that one.
All right, well, everybody do this for me quick. We got a 0 and we got a 0. 0 equals 0. That's good. Plus 25t minus 4.9t squared. Oh, quadratic, right? No, not quadratic.
Can you?
Why not quadratic?
Because you can divide out a t.
You get rid of one of those, right? So you get 25 divided by 4.9 equals t.
Almost 5.
Okay?
Can we just say
Approximately 5. Okay? 5 seconds. 5.1?
Yeah.
5.1 seconds. All right, now with 5.1 seconds, we can tell how far it goes, right? Because this is its velocity, this is the time, and why is that enough in the x direction?
Because acceleration is not.
Yeah, there's no acceleration, right? And so this equation, x equals x naught plus v naught t plus 1/2 at squared, there's no acceleration. So x equals x naught plus v naught t. And since we're starting at 0, probably, unless they tell us otherwise, then x equals v naught times t. Our v naught is 25 square root of 3 times 5.1. So what's x?
221.
What is it?
Approximately 221.
221 meters. 221 meters. Yes. All right, if you remember this equation, you saved yourself a little time, right? Now remember, this equation only helps you with this exact problem, launch and land at the same height, right? So if you happen to plug in here 50 squared sine of 60 divided by 9.8, you get that answer. Same thing. Okay? All right. Well, shoot, but right here, this bomb happens to split into 2 pieces.
Only 2?
Only 2, because we don't want to make it too hard. This is 1/3 the mass, and this is 2/3 the mass. Okay? Because it's a very cruddy bomb. Okay? And let's say that this 1/3 the mass lands over here at a distance 40 meters away from our intended target. Where does the 2/3 mass land? Will it be 20, as suggested? 20 or 80?
The center of mass has to be right there.
Okay, the deal is the center of mass still has to land on the person, right? Even though there's not anything there at the center of mass, right? So if this one lands here, is the center of mass going to be there?
No. I think it's 40.
I think
I
it is. That it is. It's
Okay, if we call this our 0 location, let's just find out.
20 times 2.
Our center of mass, the x center of mass, has to be, or center of mass in the x direction, whichever you prefer, the sum of the mr's over the sum of the m's. What's important is that this adds up to 0, right? Because the sum of the masses will not add up to 0. So this has got to add up to 0. So if I call this my 0 spot, x equals 0, and I call this positive and that negative, will this mr equal that mr? Yeah. 1/3 times 40 is the same as 2/3 times 20, right? But one's positive and one's negative. So yeah, so this one's going to land right there. Okay? Very nice. Because yeah, if this one landed way over here at 80, then this one's going to have to land way over here at 160. And you really missed it.
That'd be an incredible bomb.
That would be an incredible bomb. To split only into 2 pieces and have such poor accuracy. Okay. All right, let's talk about some of the forces aspect of center of mass, the consequences of this center of mass thing. Okay? If we're talking forces, okay, let's say we have a object and it's on a piece of paper, okay? Sitting on a table, floating on a table, okay? And you take this piece of paper and you pull the paper that way, okay? Now this object obviously can roll, okay? So what's the object going to do?
If there's no friction, it'll stay.
Okay, let's assume there's friction.
It'll,
If there's no friction, then all you have is an mg and you have a normal force with nothing else. These cancel, so it just stays put, right? If there's no friction. So let's say there is friction. So which way will friction be on the object?
forward. Forward.
Think about it.
To the right.
Think about it.
It'll be to the
It's to the left because it's
To my left?
higher.
No, to my,
But if you.
That way.
Right, to your right.
Okay, let me put it this way. If I'm standing here on a rug and someone tries to pull the rug out from underneath me, like the old saying, if somebody pulls the rug that way, which way is friction on my feet?
That way.
It's the friction on your
Which
feet.
way do my feet want to move if somebody pulls the rug that way? My feet want to move
With the rug.
that way, with the rug. Now, a lot of you are confused though. You're saying, but wait a minute, friction's going to be that way.
You want to try it with something?
But friction's
But would there be any friction
Yeah, you're so valid.
from the rug on your feet, or would it be from
And
the
then she
floor?
could do backflip.
There you go, Alexandria. Come
We're
here.
still waiting on that back.
I have a bad feeling.
Stand on this.
It's gonna rip.
All right.
By the way,
It's
so
gonna
this might
rain.
not work.
And if I pull this way, all right? If I pull that way, then her feet want to move this way.
Yeah.
Why? What's the only thing that's making her feet move this way?
Friction.
Friction. Because if there was no friction, zoop, and she doesn't care, right? She had her frictionless shoes on. All right, thank you.
The friction is in the same direction as the pull.
Frictionless shoes, we couldn't walk.
Now, remember, a lot of us are thinking about, wait a minute though, but doesn't friction oppose the way you always move?
No.
Friction always opposes what? The way that you want to, or that you are or want to slide. So which way would your feet be sliding relative to the rug? Your feet would be sliding that way relative to the rug. Therefore, friction is this way. Okay? Now that's really confusing because we're used to seeing friction always oppose the motion of the object when it's not really true. It opposes the sliding, right? It opposes the sliding direction. So your feet are going to try and slide this way, so friction is this way. Okay? So the force of friction on this is this way. Okay? All right, so what will the object do? What will its center of mass do? Move which way? That way. It has to accelerate that way. Now the object itself is going to roll though, right? Which way is it going to roll?
Backwards.
It's going to roll
Counterclockwise.
this way. The object from F equals ma, because we're interested only in the center of mass, right? The net force on the center of mass is that way, so it will accelerate that way. The center of mass will accelerate to the right. However, torque on the object is going to cause the object to rotate this way, right?
Yes.
So it's going to roll this way, but move
That way.
this way. Okay? Now remember to keep things in your mind that whenever we're talking F equals ma, all right, that we're talking about the motion of the center of mass, the acceleration of the center of mass, right? Only. So even though it's going to roll this way, it's going to move that way.
So it wants to move this way, but it's accelerating this way, but it's rotating like this. It's
Huh?
just sliding.
So it
So
could
there's
stand
arrows
still.
going all different directions.
What we need is a big sheet of carpet, and we need you to lay down on it.
I can
And
do
we
that.
will yank the carpet this way, and you'll move this way, but you'll roll. You'll be rolling like this.
I'll be asleep.
You'll be asleep
Oh,
as soon as you lay down.
Yeah, I see it, basically. I get it.
Get it?
Yeah, I see that. Now that I'm rolling, I see it. You can do a simulation.
I thought it was dead for a second.
Here you go. Here's a small demonstration.
Oh, you can do it like a pen.
Here, I need to pull it this way though. Okay, stay. All right, now if I pull. All right, the table is not level.
No.
Neither is the floor.
It was all slanted.
Stop.
Put the holes on the paper.
All right, I gotta put the hole down here. All right, so if I pull it this way, and if I do it slow enough, it obviously moves that direction, right? But if I pull it fast enough, it will roll. It will roll this way, but move this way. So I'm going to put it right here on this line, right here. Okay? So I'm going to pull it this way. See, now it rolled this way, but it moved over. Does that make
It was
sense?
sliding and
Is it?
rolling. And
Yeah.
it slid one way and rolled.
Is this a slippage problem?
So like,
Actually, if I pull it really fast, it'll be a slippage problem, and I can get it to almost stay in place.
Like the thing with the table.
Hey, is there
Yes, like the tablecloth. Okay? If I pull it really, really fast, I can
Oh.
almost leave it there. Okay? But if it rolls, it will end up over here somewhere. Here, let me do it like this. It'll end up over here somewhere because it's moving but rolling. Okay? All right?
Okay.
So it ends up over here.
Would we
So
ever
we have to
you know
calculate-
how it like it starts rolling this way, but then at some point it starts
Going the other way.
Yeah, what happens is once it leaves this, it's a slippage problem as it falls off of this and it's rolling this way but moving this way, so it skids on the floor.
Yeah, but then when it stops doing that, it starts rolling that way.
Yeah, what ends up happening is it's rolling this way, skids along the floor, and then eventually rolls without slipping in the other direction.
Will we have to calculate that ever?
I hope not. Just remember, when you're rolling with slipping, that the angular acceleration and angular velocity are not connected to the linear acceleration and the linear velocity by r, right? And that when they do roll without slip, then you have this again. You have omega equals v over r and alpha equals a over r. Okay? That's true only when you're rolling without slipping. So you would calculate your torque equation and your force equation separate, and then you would put them in the kinematics equation of, so you do this, F equals ma, and torque equals I alpha, right? You would figure out your separate ones here for when it's slipping. Then you would do like omega equals omega naught plus a t, alpha t, and I'm mixing them up. You would do omega equals omega naught plus alpha t, and v equals v naught plus a t. And you would plug this one in here, and this one in here, because that's the true accelerations of the objects. And then you would connect these two by v equals omega r. That's true when it rolls without slipping,
You
right?
connect them with T.
And then
T.
this is true whenever the time whenever that magical time is when it starts to roll without slipping. That's the one problem we had in that test that I had. Did I have everybody redo that one?
No.
The pull ball.
That test Yeah. was. That was
It was
sad.
the one before this last test you gave us.
Yeah, it was 2 tests ago.
So you had.
Yeah, everybody.
I think I had everybody redo that one. Yeah. Yes, ma'am. Oh, I'm sorry.
Oh, well, you're passive, but like the ball thing.
Uh-huh.
That's like when you shoot a ball, like when you put your finger on it, and like you put pressure down. You shoot
Yes,
it rolls
exactly.
back.
That's exactly. When it leaves that paper, it's exactly like that. It's spinning this way, but moving that way. And so
It
it's,
slows down and eventually starts rotating in the other
yeah,
direction.
so what you end up with is you have this. Here's your object. It's translating this way and rotating this way. So it's
Technically, wouldn't it
sliding, so it has friction this way, right?
Wouldn't its velocity be bigger than its angular velocity? Wouldn't it have to be? For
First of all, it's in the wrong direction.
Right. So wouldn't it?
It doesn't necessarily have to be bigger, it's just, if it's moving that way and rolling without slipping, it's also rolling this way. So if it's going backwards like this with angular velocity at any rate, it will slip. So velocity, yeah, because this will slow down both the velocity and the angular velocity. All right, we're off on a tangent. Here's our tangent. Let's see if we can solve it. Okay. you've got a ball like this, and you're going to do this. You're going to take that ball and you're going to do this thing, which you used to do when you were kids, and sometimes here still as young adults.
I still do that.
You still do
No,
that,
wait,
right?
Mr. Bruin, look what happens now. It turns around.
Stop it! I can't describe that. It's 'cause it's not exactly, because you got, and it's doing Coriolis. I blame it on the spin of the earth. No, it's because it's not exactly
In
vertical.
the middle, yeah.
Because it's off to the one side, and so it tilts. All right, so here we go. So what you have is it has a velocity this way, but it has an omega this way. Here's your center of mass. Okay, and let's find out what alpha is, what A is, and see if we can figure out where and when it stops slipping. Okay? All right, so first off, if we're trying to figure out alpha and A, by the way, we've left momentum, just in case you're curious,
Okay.
because we got on to a side topic
I
here.
thought so.
All right. We're doing alpha and A. So first off, you're going to have to find, or what kind of physics? It's not momentum. It's not energy. It's some kind of forces thing, right? So if I want to find this, I would do the sum of the forces equals ma in that direction, right? I'm going to call it the right positive, because that's the way it's moving. And this one, what would I use? The sum of the torques equals I alpha. And which way do you want to have positive here?
Well,
Yeah.
isn't that positive anyway?
Yeah.
That's why it's positive in rotation. But can I not say that?
I'm wondering. All right, we'll call that positive. I think that'll be okay. If it's not, we'll find out soon enough. Okay, so we have to, what's the very first thing, well, we just did the first thing. What's the next thing we have to decide? What do we have to do? I think I heard it. Yeah, free body diagram. So we've got an mg, and we've got a normal, and we've got friction is
To the right.
Yes. To the left.
To the right.
Right.
to your
Left.
right,
It's the exact, we just did
to
it.
your right, to your left.
To his left.
Yeah, it's to the left.
The
This is,
force
no
friction is to your left.
this is no longer on the paper, right?
No, I'm sorry. This is the problem where you take the object and you flick your finger on it, and it spins this way but shoots out from your finger.
Okay.
You know, like you do it with a ring, and then the ring comes back to you, or a ball, or whatever, or sort of. Unless you're Andy, and then it goes off the table somewhere in some odd direction, which I can't adequately explain at this point.
It jumps and moves.
It's Coriolis, that's right. I blame Heisenberg. It's all uncertain. Okay, so let's take care of this one first. F equals ma. How many forces do we have?
One.
I call it force of friction. And is it
I'm going to call it negative.
static? Ooh, thank you. Is it static or kinetic?
Why negative?
Static.
It's
Oh,
Static?
because
It's
No,
kinetic.
Is it sliding?
Yes.
Okay.
We got slippage, right? So it's kinetic. That's good, because if it was static, we'd be doomed, because we have the less than or equal to thing in the equation, and we'd have to stop. We don't have enough information. All right, it's negative. Why? Well, it's that way, and I call that way positive. Okay, that equals ma. Call that m. Aha. Can we do better than that?
Yes.
Sure.
What?
Minus mu mg.
Mu mg equals ma. M goes away. Thank you. Minus mu g equals a. Voila. That's our acceleration. Does that make sense? Is it in the right direction? Should we have a negative acceleration? Yeah, it's slowing down, right?
He goes,
Okay, let's look at our torque equals I alpha. Where are we summing our torques about?
Center.
I can do it about the center of mass. I think that would be a nice place.
Wouldn't you have to? Otherwise, you'd have to do like a pair.
Yeah, otherwise we'd have to do parallel axis theorem. So let's make this, are we gonna make this a ring or are we gonna make this a ball?
Make it a ring.
A ring.
A ring. A disc. No. No. A hoop. A hoop. Make it a ring.
A ring, a disc, a hoop.
Or a ring and disc a hoopa. Alright, how about we make it a ring?
A hoopa.
That's what you usually do this with, because
You do it with hula.
yeah, you do it with a hula hoop, that's true.
It
Spinning
does.
it
It totally
and
works with a
going
hoop.
out and back. Very good, we'll call it a hula hoop. Hula. Hula. Hula.
Yeah, that's right.
Hula.
ring.
Hoop.
He didn't write who.
Yeah, it's just hula. Hula ring. Hula hoop ring. AKA ring. Alright, so this becomes, how many torques do we have then?
One.
One. Positive or negative?
Negative.
Ooh, a negative. Okay, what's
Why
my
is
torque?
it negative?
Here we go. R.
Because we're bad people.
Well, it's true. Negative R cross R.
Wait, why is it negative?
F, I mean.
Because
FF.
Negative, yeah, R.
It's R cross F and your F
Force is going.
Oh, there we go.
So it's
Okay, and our sine theta disappears, right? Because we have a 90-degree angle between our force and our radius. Okay, so there's our torque. What's our I?
R squared.
Mr squared. What's our alpha?
Alpha.
Ooh, very good. Nobody fell for it. I was waiting for you to say A over R. But it's not A over R because we have slippage, right? Okay, so there you go. Now, does that make sense?
Yes.
Why? Why is the angular acceleration going to be negative?
Because it's slowing down too.
Because you're spinning it and it's the friction is slowing down that
Spinning.
spinning. Thank you.
It's D.
It's de-spinning. Thank you. It's spinning down instead of spinning
Alpha has
up.
to be negative.
What's that?
Alpha has to be negative.
Alpha has to be negative. That's correct because it's not speeding up as it's sliding across the table, right? That angular angular velocity is not getting bigger as it's sliding across the table, right? It's getting smaller because of friction. So we could rewrite this. Alpha equals, oh, hey, this R is this R, right?
Yes.
Oh, nice.
And
So that could be negative force. Oh, but we can do better than that.
We can.
I boxed it way too soon. I was all excited. All right, this is negative mu mg minus mr alpha.
Equals.
Thank you. Equals. Negative, double negative.
M goes away.
M goes away. Wow, even better. So alpha equals
Negative.
negative mu g over r. Sweet.
What? Isn't that A over R? Yeah.
So what's up with that?
That's because our moment of inertia was just mr squared instead of like 1/2 mr
So
squared.
it just happened to come
Yeah,
out
it just
that
happened to look that.
Wait, what? Oh, did we basically?
For a ring, it will look like that. For a disc, it would not look like that. There'd be a factor of 2 in there, right?
So,
For a sphere, there'd be a factor of 2/5, right?
so does that mean for rings it'll always be equal? No.
They're not equal
Oh, not equal, but
Alpha equals A over R.
because that's rads per second squared and that's meters per second squared, right? So be careful, not equal. Different units. All right, they look very similar.
I wouldn't do that with my ring.
All right.
Jumps.
It's not getting into that.
We want to find out where and when it stops sliding.
Kinematics.
I believe that's kinematics. Now, what do we know?
I don't know.
We know A. Okay, let's translational and rotational. We know A and alpha. What else do we know?
We know that at the same, when we stop slipping, we'll at the same time.
Okay, we do know that the connector between these two, when we have that what? Theta equals x over r, and omega equals v over r, and alpha equals a over r. All these will be true when it stops slipping at the same time, right?
Yes.
So we got time. Well, time's our variable, right?
Yeah.
So we don't really know time, but we'll be looking for time. What do we know? No.
The equations for
Do we know how fast it started?
yes.
Yes.
V naught. Do we know how fast it started?
Yes.
Omega naught. Okay, that gives you your dead giveaway. You don't know the final velocity, right?
Right.
But you do know the initial. So which equation is probably our best bet?
Ooh, v squared equals vo squared plus 2ab.
So we're looking
But
for
we don't
time.
have
You love that equation. You're the only person I know that loves that equation.
I'll get it right
So we
eventually.
can get the final velocity.
Eventually, it will be the
She's
answer.
just gonna keep saying it until she writes it.
Yeah.
Why shouldn't like avoid that
No,
being the
we don't use that
equation?
in the machine.
I'm digging this.
Is it
Like, how's
Rhetorical.
this? Jumps.
Okay, how about this? Where does it begin? 0 and 0. We know the initial velocity. We know the acceleration. Right?
Yes.
So we know this. We know this. We know this. We know this. I don't know time. And I don't know theta and x. Uh-oh, have we reached a dead end?
No.
I think not.
Just substitute one for another.
Okay, this will be true, right? When they slide, or when they get to the point where they're rolling without slipping. So I can substitute in for here, what? X over R. And I know R, and now I just have X and T as my unknowns. Okay, so probably I don't know what would be easiest. You could solve this one for X and plug it all into the other one. That looks like algebra nightmare. What might be easier for you is to plug the numbers in if you have them, and then graph the two equations and see where they cross. That might be useful. If that doesn't help out and you just have symbols, then you're kind of doomed. X equals V naught T plus 1/2. And our A is this, negative mu G T squared. And over here you have X over R equals omega naught T plus 1/2 minus mu G over R T squared. And you would take this and plug it in here and solve for time, which does not look very appetizing.
That is not.
Would it be worth it, like,
Yum.
in the end, the final equation answer, whatever, would be like 1 point and then like.
You're exactly right. Being very pragmatic at this point, if you got this far on the test, from here down to the end is going to be 1 point. At best. Okay? They may not even give you an answer for the point for the final answer if they just feel that you've already done all the physics that you need to show.
The rest is just algebra.
Because the rest from here on out is just algebra. That's correct. It's just, quite frankly, it's busy work. It's using a tool to finish the job that you've already figured out. Okay? So that might be a good place to quit as far as making sure you finish the rest of the test. Especially, you really have to be aware of this on the AP exam in Physics C. Because on Physics C, you get 3 free response only. Okay? And 45 minutes. Now, that seems like, yay, it's a shorter test, but you remember, you have less room for error then, right? That means if you take too much time on one problem and you miss, and you don't do one, that's 1/3 of the problems if you skip one, right? If you skipped one on Physics B, that was 1/6 maybe. So it's not as big a deal. So you really need to make sure on the AP exam that what you do is you start with the problem that you know the best, and then work your way towards the more difficult one. And try to make sure you have a chance to work them all. Yeah.
Isn't it 3 problems per test? So if you
Yeah, so
understand what's-
but you get a grade for each half, so Well, it's nice because you get two for the price. Well, you don't really get two for the price of one, do you? You got to pay for both. But you get two chances for success for one class. All right. Another thing, everybody, you could use this center of mass idea. We're going back to center of mass idea. Is, let's say you had a boat or a raft, and you're standing on one end, and Mini-Me is standing on the other end. Okay? All right. Where's the center of mass of this thing?
To the right.
Somewhere over here, right? Yes. Okay. Now let's say that the two decide to swap places on the raft. So you walk this way, and Mini-Me walks this way. All right. Assuming there's not a lot of friction, outside force, essentially, from the water. Thank you. What will happen? Think of center of mass.
As they move, the center of mass
Yes,
gets
doesn't he
closer.
have
Is it a
to
gondola?
If there's no net outside force, no matter how fast you walk, whether you walk fast or slow or whatever, as long as there's really no net outside force, if the sum of the forces equals ma, and this is 0 for outside forces on the outside, then the acceleration of the center of mass will be 0. So that means if they jumped to the other position, high-fived in midair, then what's going to happen is the boat will have to move over like this, right? Or the raft. So that big person is now here, and little person is now over here. So the center of mass, oh, I missed it. Center of mass is supposed to be in the same spot.
So wait, the boat moves?
The boat will move, that's correct.
I really
Okay.
like it.
Now, if you've ever been in like a small boat, if you've ever been in a small boat, like a raft or something, or a canoe, or like a little fishing boat or something, or even a ski boat, and if you've ever tried to get off the boat and go to the dock, you know immediately that when you walk one way, the boat goes the other. Because you go a normal step and you miss the dock. Because the boat has gone backwards. As you push back, the boat goes back and you go forward. Now, if the boat is really big, like a big ship, a cruise ship, you walk off the cruise ship, that cruise ship is going to accelerate backwards tiny, right? So you don't notice it. The smaller the object is that you're on,
So a bunch of people ran off
that's correct. So if everybody said fire, fire, and everybody ran off the back, the ship would move. In fact, here you go.
That should have been that entire conflict because it moved the other way.
Back,
The iceberg.
the really big ships back in World War II, they had these huge guns on the deck.
Yeah.
Huge guns on the deck. Okay, when they would lob these great big shells that way, the ship would recoil. And they could not shoot them all at the same time.
Because it would capsize.
I don't know if they would capsize, but it would certainly not be good. Okay? I think it was too much force on the vehicle itself, on the ship itself. But in theory, yes. In theory, if you launched, a bus at a high velocity, yes, in theory, you could flip the ship over.
I launch a bus.
Okay? Yeah, that's right.
I should go launch a bus off a boat.
That's
Do
right.
like applied physics.
What if you just
Like,
All right?
Actual application.
Because the center of mass of the object must stay in place. Okay? Yes.
So I guess if you wanted to, like if you didn't have any bombs at the time, or any like shells.
You could shoot a cow. Sorry, Monty Python.
If you just, that's what I was thinking. I haven't seen one of those yet.
Run away! Run away!
Yeah, if you were able to get a bus on the enemy ship
Yes?
and drive it really fast off the ship,
Yes?
you could kill everybody.
You'd make the ship move the opposite direction, but I don't know if that would kill anybody.
I would just ice storm.
You might give them all whiplash, and they'd all have to wear neck braces.
I would hate to get the whiplash on the ship. Could you theoretically drive the bus quick enough that it capsizes the ship?
It depends on the size of the bus.
You have 5 buses.
Okay.
And the speed of
Well,
Shoot a bus and move.
so what about like, whatchamajigs? What are they called?
Whatchamajigs?
Aircraft carriers.
Yes.
If they launched like 5 planes.
The
And
But
aircraft
they
carrier is
don't
way
launch
too
them
big.
all at the same time. They alternate.
Okay, here.
That's a huge map.
Here's an easier example. You're standing on a skateboard. You jump that way.
Oh, it goes
And
that
I
way.
hit my face and break all my
Face plant.
teeth.
Yeah, faceplant maybe if you're not prepared for what's going to happen. But you jump that way. What happens to the skateboard?
That way.
Which one moves faster? Skateboard, because it has less mass. The center of mass of the system didn't ever move. Center of mass stays right here as you fall that way, and the skateboard rockets that way.
Hits another person.
Okay. This is the same thing as with a gun. If you take a gun, you shoot a gun. Not that I'm advocating that. All right. What happens is the bullet goes forward, the gun goes backwards because the center of mass of the system never moves. All right. Now the same thing is going to be true. Actually, we're going to get around to this, but we're in momentum, and this is all going to move around to the fact that here. We talked about the location of the center of mass, the x location of the center of mass, and even the y location of the center of mass, right? But there's also, you can track the velocity of the center of mass, okay? The velocity of the center of mass, say in the x direction, is going to be, if this is equal to integral, let's do it just the easy way. The sum of the mx's over the sum of the m's, and this is the sum of the my's over the sum of the m's, right? Okay, if we're going to find the velocity of the center of mass, guess what it will be? The sum of the mv's in the x direction over the sum of the m's. What's that? It's momentum, okay? So, in the absence of outside forces, if there's no outside forces, that means there's no accelerations. If there's no accelerations, the velocity stays constant. If the velocity stays constant, that means that even though individual parts of the system may be changing velocity or momentum, the velocity of the center of mass of the system never changes. Now look, if you move this to the other side, you get the sum of the mv's of the center of mass equals the sum of the mv's in the x direction. And so what you end up with is in the absence of outside forces, the sum of the mv's before and the sum of the mv's afterwards are the same. The velocity of the center of mass never changes, which is another way of saying that the momentum never changes. Okay? All right. So what happens is if you have a car crash and you have like a car like this, another car like this, and let's say that this one's moving this way slow and this one's moving this way fast, okay? Where's the center of mass of the system? Well, somewhere in between, right? The center of mass of the system will have a velocity.
Because as the cars move.
Because as the cars move, this moves, right? Now, this one's moving slower, this one's moving faster, little v, big V. This V is going to be somewhere in between, right?
Yes.
So it's moving to the right at an in-between velocity. Okay? Now, when these two collide and maybe bounce off or maybe not bounce off, this center of mass never changed. It just kept going at the exact same speed the entire time.
So the
But
center.
then, so what happens after they crash? When they stop?
Well, that's if there's friction, they'll stop. Right?
Oh, okay, so we're talking about.
Because if
We're
they,
talking like, you're right. Now remember, there can't be any outside forces. So we're talking like, if there's friction during the crash, we're talking like right before the crash to right after the crash, that won't be changing. But then friction is a force.
When they stop, then the center of mass stops.
Yes, correct. That's correct. Yeah, right.
I
Yeah.
have like a picture of in
Yeah, like if I stop, my center of mass doesn't keep going.
Oh, crap.
I lost it again.
No, come back. Hey, that's one way to lose weight. Yes.
It's because I remember how you were saying how it keeps moving, so I was trying to figure out, I was like.
No. The center of mass never changes in a collision like that.
Very funny.
So like, if you think about that for a second here. Okay, think about this. When these two objects collide, and let's say they stick together. So you got two cars smashed together.
On top of a boat.
No, not on top of a boat. Okay, where's the center of mass now? Right here. And guess what that velocity of the center of mass is? Whatever this was. So all you have to do is figure out the velocity of the center of mass beforehand, and that's going to be the velocity of the combined mass afterwards, right? Oh,
So,
kind of slick.
one part's going faster, the center of mass equals.
So let's just do that since we know conservation of momentum. Let's say the mass of this car is 2,000 kilograms. It's a big car. And we got 1,000 kilograms. Say the velocity of this one is, velocity here is 3 meters per second, and the velocity here is, 12 meters per second. All right, what's the velocity of the center of mass right here? Okay, velocity of the center of mass will equal the sum of the mv's over the sum of the m's. Okay? So what's this mass? 2,000. What's its velocity? 12. Plus 1,000 times 3. Now notice if they were going in opposite directions, we'd have a negative sign somewhere, right? Over 3,000. So what is that?
9 meters per second.
9 meters per second. Now, since the center, if they hit and stick together,
That'll be the velocity.
that will be their velocity. So let's figure it out from conservation of momentum. Momentum before equals momentum afterwards. mv plus mv equals m plus mv. Does everybody see that we're going to be doing the exact same math?
Yes.
That this is m plus m moved down here, and that this is literally the velocity of the center of the mass, right?
Yes.
Yes, we could have been doing this last year and the year before. Actually, that's what we were doing. You just didn't know that.
That's crazy.
Isn't that crazy? It's like in a crash. If you look at like pool balls.
That's an extreme pool.
All right, and this one comes rocketing this way. Before you begin, all you have is this mass moving at that velocity. So there's the velocity of the center of mass. After they collide, before they hit the bumpers, okay, before they hit an outside force, this center of mass continues to move this way after the collision, and they all start flying everywhere.
But I thought you said the center of mass doesn't
Okay.
move
He
without.
goes.
But there's
There's a force.
a force when it hits. Right?
Yeah, they're going to hit. These are all going to take off. But the center of mass of the system will continue to move that way at that velocity until they start hitting the bumpers.
Until
Not
one
for
of
long.
the
Yeah, until like one of these hits this and bounces off, then it's all messed up.
Mr. Broom,
They'll get an outside force. Yes.
is there any way if you had a frictionless pool table and if all collisions were elastic, that you could like do a mathematical equation and like configure this machine that you hit the ball once and everything goes in a hole?
Yes.
Yeah, we can do
Yes.
that without all that.
Yeah. No, I'm not that great at pool, but yes.
Definitely.
In theory, yes.
That would be
Do it, Andy.
the best.
Actually, how many? I know you can set the pool balls up in a certain arrangement, and you can hit them, and you can get nearly all of them to go in.
Andy,
Get it just right.
friction, there's only one person that plays. There's only one person.
Right.
And if you hurt
Where's
you,
Minnesota Fats when you need
Because I
them?
was winning.
Infinitely until
And we need Wisconsin medium build.
That's what
Yes.
True.
They were never any other person to go keep that.
Not
Oh,
really.
when they stop, they're not stopping.
Pretty much the same thing as
We
before.
have to have elastic.
But we were fun
Yes.
game.
No, but you gotta make sure that 8 ball goes in there.
The center of mass is between the two.
Yeah.
Throw it in the
The center of mass is just in the one full ball because the other one's not moving.
Yes. The only reason the center mass is right here to begin, you know what? You're right. I was incorrect.
Yay!
Thank you for pointing that out. Where's the center of mass of this system? It's probably somewhere in here.
The 8 ball.
Could be the 8 ball.
They were thinking of physics when they did that.
Maybe. We'll say the 8 ball.
So we really
Technically, wouldn't you have to include the Q and the person?
Yeah, you include this one over here. Now, will the velocity of the center of mass be the same as the velocity of this ball when you start? Why not? Because you're dividing by the total mass, right? Okay, so when you hit this ball, the center mass velocity over here is going to be smaller. In fact, it'll be 1/16. Right?
Oh, yeah.
Because there's 16 total balls and you're only hitting one of them with a velocity, right?
But the white ball weighs
So why is it so important that you hit the cue ball incredibly hard?
to get that 8 ball in.
Because it's going to be divided by 16 for the center of mass velocity, right? And so unless you hit it with some substantial speed, this whole group is not going to do much. Gia, thanks for pointing that out because that was incorrect what I wrote down here. The center mass of the system is over here, and the velocity of the center mass of the system is quite a bit smaller than the velocity of the cue ball. Okay? It's going to be my lovely assistant. Can you hold that? I just hold it right here. And hold it tight because, here, no. That's slack. Okay, now, when it rolls, okay, that's going to, you're going to pull that pin out, okay? You ready? You ready? You ready? Oh, wow, that didn't fly up very high. That was very anticlimactic.
Push it down further.
Oh, the ball is gonna
Here.
go. This,
You know that was right.
is it the
There we go.
It's not that hard to stand.
Don't push it in. No, don't push it in very far.
There we go.
I'm sorry.
You just messed it up.
I got this.
I've been calling you since like 4 years.
Oh, that's not going to work. That's going to get stuck.
I'll take a picture.
All right, you ready? That one got stuck. Andy, you broke it.
I broke it.
How did I broke it?
Wow, Megan.
You broke it.
That's not fixing
Jiggly, you wanna roll?
See, I can't do that.
That's how I fixed my team.
When did?
It's not a weapon. It's a tool.
That's what they all say.
So there's one.
It's a tool for
It's a tool for murder. No, it's not a tool for murder. It's a
It's a tool for punishing bad things.
She goes, okay.
tool for punishing
Or
bad
for
things.
eating.
Who said that?
Yeah.
Why is it getting stuck?
She goes, okay.
Okay, so
See, buddy.
I don't want to hear a random story.
It all fucking happened.
Anybody have a marble?
It got stuck.
All right, you ready?
We were playing marbles just out in
Physics doesn't exist.
I've been trying
It's all
I blame it on Cindy.
I think that they were supposed to catch and land back. If that was true, I would really be mad about like
Maybe she has her hand right behind it.
Physics has lied to me.
physics
Again.
makes us all
Damn. Ready? Man, I thought I'd wasted my life.
That would have been a lot of unnecessary tears.
Every time I'm this close to
How do you get there so fast? Oh my god. That was just a second and he moved that.
the center of my.
He's such a master boy.
The instant where you're floating.
Okay, everybody, here's case number 1. Please, or case A, please calculate the velocity of the center of mass. Go.
Is that? Are they both 2 kilograms or 3 kilograms and 2 kilograms?
3, 2, 3, 2. That's why I have 3 and 2.
It looks kind of
Like
like
a 2.
No, it'd be more, right?
Oh, wait a minute. We're going to make this 4. What? How can that be a 2? That's a 3.
It's 22.
No, it is. Alright, whatever.
Sorry.
There you go.
Added and then divided by.
That's a full 3. Good job.
Boy.
And we're trying to find the velocity of the center of mass. What are we trying to find?
Is that better?
Yes.
Velocity of center of mass.
The sums of MD over the sum of
You can answer it several ways. This second one you can answer several ways. You can either answer it in component notation like IJ, that would be easier, or you could answer it in magnitude and angle. All right, so this one, what is the velocity of the center of mass?
5.2.
5.2 meters per second. Correcto.
3 plus 2 is 5.
Wait, what?
It's 5.2.
Yeah,
I got it
0.8.
right. I got it right.
It's 5.
Right? The sum of the MVs over the sum of the M's. So you get 3 times 6
Get a relative to
plus 2 times 4
Negative.
over 5.
Yes.
Okay? 5.2. All right, now this one. Okay, this one's actually really easy to solve if you put it in component notation. Because what's the center of mass doing in that direction? It's just m times v divided by m, right? So the velocity of the center of mass, oh, is it really?
No.
I said 0.8.
0.8?
Oh wait, how much? We're doing B?
All right.
Never mind.
Velocity of the center of mass equals the sum of the MVs over the sum of the M's.
So they both.
What's my MV in that direction?
Because 3.6.
18.
Take this.
18.
Oh, the mass.
What's
is
my total mass?
5.
5.
Thank you.
So what do we get?
3.6.
3.6 meters per second. What's the, that's in the x direction. What's the velocity of my center of mass in the y direction? The sum of the MVs over the sum of my M's, which is going to be, this is my only MV in this direction in y, so it's going to be what, 8 over 5.
Negative.
Ooh, negative 8?
Just for fun. No.
All right, I'll buy that. If we're doing standard X,
Let's
Y
not have
coordinate
fun.
system. So what is that?
I don't
1.6
like
meters
being
per
kind of
second
fun.
negative. All right, so your answer would be velocity of the center of mass equals 3.6 meters per second I minus 1.6 meters per second
J.
J. Now, if you wanted to, you can convert that into magnitude or polar coordinates, which would have given you 3.94 meters per second at an angle of 336 degrees, because it's in the fourth quadrant. Okay?
Unless you did the thing where you were positive, it would be in the.
Oh, if you did the negative angle?
Yeah, it would be in the first.
Okay, so
Yeah, but negative.
How did you get the angle?
The angle is, because you get this, 3.6 this way, you get 1.6 this way. So, and then this is your angle that you'd find, but that's in polar coordinates, that's all the way around this way, right?
Oh, okay.
It's in the fourth quadrant.
Okay.
Okay, question, Andy. Andy,
never mind.
got it?
I think so.
All right, now, all this stuff is fine and dandy. Let's, it's kind of cool to think about things in terms of center of mass. And center of mass does show up on our exam. Like, it's not uncommon for them to give you a problem like this. And they ask, where's the center of mass of this object?
Oh.
In the hole. It's gonna be close to
All right, everybody moaned, so we must do it now.
So it's gonna be like,
I didn't know I could in the hole.
Okay, this side is 6, this side is 1, 4, 3, 4, 2, 6, and 6. Those are the dimensions of the sides.
There's 3 sixes there.
Oh my goodness. And this adds up to 6, so we're okay.
it's the devil.
Salvador,
They
no.
said that the top of his desk is the bottom. Oh.
We'll do that next, now that you've asked.
Is it uniform?
Okay, it's a uniform density.
Okay.
If it's a uniform density, then what do you do?
Divide each by 2 and it's right there. No, just kidding.
I guarantee you it's not here. By the way, if this is a multiple choice question, a really good strategy is to do this.
Hang it.
There's the center. Which quadrant is it in?
Upper left.
It's not
It's
in.
got to be up this way and this way, right?
Yeah,
Yes.
that sounds good.
So it's got to be somewhere up in here. Maybe not where I've drawn it, but somewhere up here. So you look at the 5 answers. And if the 5 answers, if there's 1 here and 1 here and 1 here, then you throw those away immediately, right?
I don't understand, like, how did you just say it's there?
Because there's more mass above this line than below. There's more mass to the left than to the right. So I know it has to be somewhere in there. Okay,
Or can we like construct it and then spin it and see where it spins?
you could, or you could hang it from the corners and
Where would
see,
you
draw
pull
vertical
that out
lines.
from?
Because you can't balance it, maybe, because it may be right here where you can't balance it, right?
No, you must think.
I would cut that out of the test. I would rip a little C and then hang it.
I do this, and you videotape yourself with your camera, and then stick your camera on the test and turn it in.
Well, no, you can rip it out of the test book and then like hang it and drop it.
Your lanyard? Use your lanyard.
Using my SEM lanyard.
When you turn in the test, you just
All right, you knuckleheads, how do we really solve it?
You break it apart.
Break it apart. Here's how I broke it apart. Okay, where's the center of mass of this piece?
Right in the middle.
It'd be 1 and then 0.5 and then.
It's at 3, 1/2.
Yeah.
Okay, where's the center of mass of this part?
It's at
What?
1.5.
Okay, it's at, this is 4, so it's at 1 and,
1 and
1.5.
okay, this is 1.5, but I have to add 1 onto that, right?
2.5.
If I'm calling this my starting point, 0, 0,
So 2.5?
so that would be 2.5.
Oh.
Where's the center of mass of this thing?
3
3.
and
3 and,
5. 1 plus
Okay.
4.
yeah, 1 plus 3 plus 1, 5. All right, so here we go. Now, in the x direction, my x center of mass is the sum of my x m's over the sum of my m's. All right? Eventually, yes.
but not now.
The units cancel, but these m's you can't cancel. Okay, what's the mass of this thing?
That's a good question.
About
Now, if it's a uniform density, you
So
can
can
kind
you
of
get-
make up a mass based on its area, right?
so area
So the mass of this one is going to be proportional to 6 times 2, or 12. The mass of this one is going to be proportional to 3 times 2, which is 6. The mass of this one is going to be 6 times 1, or 6. So there's my mass.
Oh boy.
So my total mass is going to be
24.
24 of these pieces, 24 of these little, whatever they are, right?
24.
Okay, this one is going to have an XM of 3 times 12. 3 this way times its mass. This one's going to have an XM of 1, plus 1 times its mass of 6. And this one's going to have an XM of 3, that's its location, times a mass of 6 as well. So, that's 4 times 6,
24.
4 plus 36.
36. So 50. 60.
60.
60 over 24, what's that?
Magic.
2.5.
So 2.5, does that seem reasonable?
Yeah.
Okay, it's to the left of center. Okay? So then we have to redo this for the y. The y center of mass is equal to the sum of the y m's over the sum of the m's. Okay, do that one.
It's in the hole.
You get 3.25?
Yes.
Okay, 3.25 meters or units or whatever we have here. So is it in the hole?
Yeah.
Yeah, it's in the hole. It's somewhere in here.
Someone told you.
Okay? Or as Bill Murray would have said in Caddyshack. All right, now. Caddyshack quote. All right, so here you go, everybody. Here's your assignment since the question was asked. What do you do if the object has non-uniform density?
Make you want to cry.
Cry.
You say you only have 30 seconds left.
Skip it.
Here's my non-uniform bar.
Okay.
I'm going to call this side 0. Lambda is the linear mass density of A times X. Remember, lambda is the linear mass density. Okay? All right, so AX. So at this end, there is no mass. And at this end, it's very heavy. Okay? So there you go. I want you to tell me, starting from this end, how far over do you go to find the center of mass?